It's a pleasure to come and speak to you on the Indian Space Astronomy Program. However, I must tell you at the very outset, I've retired from ISRO. I'm on as a consultant and as an advisor and as a professor there. So what I speak is largely my perspective. Of course, keeps in line with what the Space Agency is also planning to do. So let me begin. Thank you. All right, so let me begin with the kind of space research that every country begins, and that is largely the access to space was a critical issue. So we begin with small rockets and balloon experiments, and of course, finally gravitated to satellites. And here is the first Nike Apache rocket flown in 1963. Remember, 57 is when Sputnik went up. So 63 Nike Apache rocket, where the rocket was actually provided from the US and had a payload. And the payload, interesting, was from France. It's a sodium vapor emission payload. The second Nike Apache flight also had a French experiment. Then, of course, we built satellites, and this satellite is Algebra, the first satellite that we built indigenously, flown from Russia. This was in 1975. Today, if you go to Trivandrum, typically you see this sort of crowd on the days when the sounding rockets are actually launched, so that the Tumba rocket launching program continues. And clearly, the program for this was actually set up by two major visionaries, Vikram Sarabhai and Homi Bhabha, great friends, and I think they colluded, collaborated in many aspects that has actually impacted Indian science and technology for years to come. But certainly the drive and the focus with which the two really established the space program, defining its fundamental approach of need to really look at resource mapping as a very key area for Indian space, while the country was still at the early phase of its growth and development, has actually led to what is today ISRO. So the 6 decades of ISRO, if you were to look at it, began with the 63 sounding rocket. And then in 75, we had the opportunity to do it. We're still building rockets at that time. Our own rockets were not yet ready. And but then with a series of other satellites using Indian rockets, we had the SROS, a series of satellites. And one of the important things from a space science point of view was this was a time when gamma ray bursts were very mysterious. They're mysterious even today, but they were much more mysterious then. We didn't know whether it was in the galaxy, in the edge of the universe. We didn't know where it came from. So you had to use triangulation techniques to actually locate them. And SROS too carried these sodium iodide gamma ray detectors that actually was used as part of the triangulation process to locate gamma ray bursts. And then optical astronomers would have to spend years trying to map out the error box because it's such a large error box in these things. But gamma ray bursts have moved quite a bit since then. In '96, we had an opportunity to fly X-ray experiments on a remote sensing satellite. By that time, remember, the focus was remote sensing. So because of remote sensing was a major requirement of the country. So whenever you have opportunities to use that platform to do science experiments, ISRO permitted that. And Professor P.C. Agrawal from TIFR, with the team, was told, okay, you have 9 months to deliver a payload. They did it in 9 months. They did put it together along with the group at the ISRO Satellite Center. So that was sort of the IXAE experiment, which was primarily proportional counters, looking at X-ray binaries, trying to look at timing and spectroscopy. But it is critical because it is that experiment that showed that the community in India is actually mature enough to really build serious science experiments. And then Professor Agrawal, Professor Kameshwar, etc., joined hands to really argue for a major Indian astronomy satellite, which became ASTROSAT. Many years of discussion and nearly 20 years of development. And in 2015, we flew ASTROSAT, which continues to fly today. But prior to ASTROSAT, we had opportunities also around the same time. The moon was a topic of great interest, and planetary exploration was something that was felt by both academics as well as technocrats in ISRO that is worthwhile for us to do. So the first lunar mission, Chandrayaan-1, which also which was very collaborative experiment. It's very, very interesting that at that stage, sometime in 2003 or so, it was decided that we'd open up opportunities for global partners to participate in the Chandrayaan-1 mission. So payloads from other countries were proposals on that were solicited, and 6 payloads were actually adopted from other countries. And then together, along with the experiments from India, it was flown in 2008. So in 2004 is when we had that other meeting in Udaypur. So that was in 2008, and that was important because it is in many ways one of the modern space science history for India. This is actually the first mission that actually set the ball rolling with regard to science as a major program and an observatory of that class. Then we had a mission to Mars, Mangalyaan, Mars orbiter mission, which was actually primarily a technology mission and did carry 5 experiments on board, but the focus was getting into Mars is no joke. Getting injected into it, etc., was a major concern. So it was done fairly rapidly, and so the technology focus was the primary focus of the mission, and the experiments which carried color cameras and a few other things, and discuss in a few minutes, continued until very recently. The mission was actually terminated recently. We then had the ASTROSAT launch, which I talked about, and then in 2019 there was a Chandrayaan-2. It's a very large program. It took 10 years for us to really get from Chandrayaan-1 to 2, because now this involved not only just an orbiter, it also had a lander, as well as a rover program. And as many of you know, we were not really successful with the landing program of Chandrayaan-2, and which is going to be repeated with or retried with the Chandrayaan-3 later this year. And then we have, of course, some of the future programs. So in yellow are the 2 missions that are currently, science missions that are currently in orbit. And these are the future programs that I discussed. So the Mars orbiter mission, as I mentioned earlier, was primarily a technology demonstration mission. And the key was to really make sure we get inserted into the orbit. We had to really worry about deep space communication. We haven't gone this far. Autonomy was critical. It takes time for light to travel for a command to go from here to there. And so you can't wait for feedback from the housekeeping saying that, yes, the temperature or that the voltage has gone to this level before issue the next command. So it had to be built on board. So autonomous features were incorporated. So those technologies are all worked out. Scientifically, there was also clearly objectives of looking at features. It didn't carry a very large camera. So it was primarily an off-the-shelf camera, color camera that actually was used to look at Mars in total. Many a time, when you go to, as things advance, as it happens even with regular astronomy missions, where you get so sensitive, they can no longer look at bright objects. And so it's similarly in imaging processes. People have cameras with very high resolution, but small footprints, so you can never get Mars as a total. And this camera actually gives you pictures of Mars in totality. And that is used. And then it had a few other experiments, primarily look at methane. Methane was at that time seen as an interesting signature. There was an evidence for methane detection, but we were not able to confirm it. And then we had, an infrared camera that was actually used to look at the near infrared imagery from Mars. So it completed 7 years, and early this year, while it had a little fuel left, it lost, it was difficult to control it. It was a 6-month mission, but lasted long enough. And this sort of broad pictures are available. And there was a big dust storm that was seen during the mission phase. That was interesting results have come regarding how atmospheric escape can actually happen from dust storms. ASTROSAT is a running satellite, very successful, 7 years plus. And has 5 experiments on board. This is the picture of the satellite before launch in the clean room in Bangalore. 2015 launch. It was launched in the circular orbit, and unlike other ISRO missions where you often have for remote sensing, you use a sun synchronous orbit, an orbit where the sun and the orbit plane makes a fixed angle, and so that when you image Earth, you always image at fixed solar illumination conditions, which makes it easy to compare day-to-day images, etc. However, that particular sun synchronous orbit, which has the polar orbit, has problems of high background which affects detectors. And so when you're trying to do astronomy, you really like to do it in a lower orbit, in particular X-ray instruments. So ASTROSAT was specifically, the scientists requested a very low inclination orbit, 6-degree inclination. And so that was achieved with ASTROSAT. And that enabled us to really have much longer duty cycle of operation of the X-ray instruments. It had many experiments on board, and there will be a detailed talk, I understand, later that will discuss this. But in terms of targets, you have, I put solar system in brackets because we still try to do the solar system. And this comes back to the point I mentioned earlier. Many objects in the solar system are too bright for our ultraviolet telescope to look at. But for example, we like to look at the moon with the soft X-ray telescope, but you have to make sure that the UV instrument is not affected, and that we can track something that's moving so fast, unlike our regular tracking of astrophysical sources. But clearly there have been observed interesting results, and from exoplanets to stars to binary systems. A lot of the X-ray data looked at the galactic plane with a lot of X-ray binaries, microquasars, star clusters. Milky Way as a specific focus, and of course the Magellanic system has been an area of great interest. And then we start forming in active galaxies, clusters, transients, and so on. So I won't say much more about it other than to say that it clearly demonstrated the UV instrument that this institute was involved in delivering, clearly showed that it can actually produce very high resolution images, large field, high resolution images. Today, best of it comes from this instrument on ASTROSAT. And those results, I hope, will be presented elsewhere. In terms of user community, this is one of the rare cases we have a very large user community. We have 30 registered from France and large numbers from US and Italy. But there is an open call for proposals. There is a review every year. I forgot end the cycle of AO now, but there's been many. And the data are all accessible from the data center that we have in Bangalore, the Indian Space Science Data Center. And we have regular meetings that actually are enabled to allow the young researchers from universities, institutes, etc., to come and actually present their papers. So that's a satisfying part of this whole program. Let me move to the Planetary Exploration Program. This is Chandrayaan-2, the satellite, and that is the lander and the rover inside that. Mated together is a very large satellite. You can see a person standing next to it. So maybe one of the tallest we've actually taken up. So this is just before launch at the Dakota. This is the fairing of the rocket in which they make sure all is well. And its focus had primarily 3 thematic areas: water and moon. Now, water in Chandrayaan-1, we were fortunate to have a experiment that actually could demonstrate the presence of water on the moon, not just in one location, but globally present. And it was important to focus on that a bit more, because water on moon is no longer just for science with regard to origin and evolution of the moon, but also for potential human return and as a potential launching platform for future missions that go to Mars and other places. Water is critical. So you need to look for surface water. And so we had an infrared spectroscopy instrument that actually looks at in the near infrared, about 1 to 3 microns. And close to 3 microns, there is an absorption feature that is characteristic of water. And that is what was used in Chandrayaan-1. However, because it involves also corrections to thermal component that will come into the same band, and that subtraction was challenged at some level, because they need to really go to broader energy bands up to 5 microns, independently derive the thermal component from that, and then do the subtraction, and then demonstrate that the water signature is indeed there. And that is what was done with the IR spectroscopy instrument called IIRS. Was launched that extended the water signature, the spectroscopic signature capability down to 5 microns. We also had synthetic aperture radars, which are very good to really probe subsurface, because at S band at 1.4 and 2.5 gigahertz, these frequencies can actually penetrate a few meters, and you can the reflection from the return signal that the SAR sees tells you much more about potential water present in these places. Of course, surface roughness can also provide backscattering. So you really look at it from a polarimetric perspective. And so we had launched in this mission a SAR that had both L and S band. And I think the L band is for the first time flown on it. Having multiple frequencies allows you to actually remove some of the degeneracies that exist with a single frequency observation, which has been the past experience with Chandrayaan-1, with LRO, etc. They had some frequency experiments. We also had in the exosphere of Mars, which of Moon, which is a very thin presence of molecules. We actually have a mass spectrometer, a very sensitive mass spectrometer that can look for, in principle, many molecules, including water, argon, and so on. So that is also there. So water on Moon was addressed by these. Then there's also global mapping. As this is an orbiter mission, it actually maps it. We look at the mineral composition, again, for the spectroscopic signatures and absorption features that demonstrate that are characteristic of a combination of minerals. As usual, you can take in the laboratory, you can actually take ilmenite and actually illuminate it with optical light, and then look at the infrared spectrum, you get a very clean signature of ilmenite. But when you have ilmenite combined with pelagic rays, feldspar, a few other things, you can get a confusing picture. Just as we do in astronomy, you come back and ask, what is the fractional contribution of these? And that is remained a challenge, but we made a substantial improvement of that with this IRS mission. And then you also look at the same element, not in the form of mineral, but the element present in the mineral, independently as a chemical signature. You actually ask, can I identify the extra transitions that actually come from these excitation of these elements? And this could be magnesium, aluminum, silicon, sulfur, calcium, titanium, iron, and so on. But to eliminate it, you will need an X-ray source, and you don't have an X-ray source with you that can be operated from a 100-kilometer orbit. So you use the natural X-ray source, and that is the sun. The corona of the sun is sufficiently bright, and during a flare, it gives you the extra light that you're looking for. So whenever there's a flare, you look at the reflectance, X-ray fluorescence line coming from the surface, and that is the class experiment. And so it combines that with the solar X-ray monitor, which has been used independently to do interesting solar science with regard to solar flares, the first ionization potential effects that you see in coronal abundance, and so on. You also look at the SAR is also used for the thickness of these regolith, topography with the imaging cameras. We have a stereoscopic camera, as well as a very high resolution camera. Then you also use the transmission, the orbital, the spacecraft communication channel. As it comes to Earth, as it graces the edge of the planet, we can actually learn things about any ionized content in the environment around the planet. In this case, the Moon. It was also an attempt to do localized mapping, because remember we had a lander and a rover that was meant to do localized mapping of the landing location and maybe a little bit of probes that included properties of the regolith in terms of conductivity of the thermal conductivity of the location, plasma environment. Actually had lander probes, and something that actually looks at the alpha particle spectroscopy that actually tell you compositional information. We also carry something called LIPS. It's a laser. What is that? Laser induced ablation spectroscopy. And what is done is you basically shine a laser and they allow the surface of that material to actually become a plasma, and then you look at the spectral signature of that. And that is also carried on it. And of course, there's a seismometer. Unfortunately, as of now, this is not complete because of the incompleteness of the Chandrayaan-2 mission, and we hope to have that addressed in Chandrayaan-3. So it's a simple 100-kilometer orbit, and we just mentioned these experiments that are on board. Here are some images. Maybe it's difficult to see, but you can actually see small boulders. This is coming from a camera called OHRC. It's actually a very high resolution camera. It has a resolution pixel, of 25 centimeter resolution. It's sharper than what is even there on the NASA's LRO mission. So we've been actually providing data using this camera for future landing programs. Japanese wanted a landing imagery of their landing location. We provided that. Very soon we may be providing that for the Artemis mission that's actually landed in the ports. So, but it's very good to really see very small features in terms of small crater counts, boulders, in terms of, and you can, if you look carefully, you see the shadow from the grazing incidence of the sun. So illumination is critical in looking at optical imagery, but it is a very small footprint, so you can't use it to map the whole moon. And it demands a large data volume. So you can't operate it all the time. So a real challenge on Chandrayaan-2 is to really figure out which ones to operate when, and given the power condition, given the data download scenario. So it's a tricky thing for the mission to really do. The other camera, which is a terrain mapping camera, which, as I said, has 3 triple cameras, 4 nadir and aft. So you take from 3 different directions, and the same spot is looked at from 3 different angles. So you can make your digital elevation models. And that is used to really look for interesting terrain. And this is supposed to do the full mapping. And I think they're almost at the end of finishing that. These are some individual images, resolutions that are, and when you look at optical images, you often find the sun elevation makes a big difference to what you see. So many a time, the same target is actually captured in different sun elevations. Now, the evidence from lunar water, as I mentioned, this is the data from the Chandrayaan-1 MQ mission, which showed a large presence of water from poles to pole. And the synthetic aperture radar on that, which was only in S-band, showed presence of water, but then there's questions because of single S-band radar. And there was also the lunar, the LRO mission, reconnaissance orbiter, that's still orbiting the moon. They were able to see glint from what appeared to be the reflecting frozen ice surfaces, both from laser as well as they have an onboard laser that is used as a measure to do laser ranging. And there was also, so they could look at this data and actually show that there is frozen water at the poles, and that is also another indication for human landing the poles, because that's the source of water. The pole is critical, and the pole is important for moon because in other parts of the other latitudes, mid latitudes and non-polar regions, what happens is you have a 14-day night, and this night is very cold, super cold, 100 degrees Kelvin, and you really have a hard time trying to really manage instruments going from 330 to 100 degrees. But at the poles, what happens is because of the grazing incidence and the orientation of the moon, not as tilted as much as Earth, you actually have some locations, some small mountain tops where sun is there most of the time. And these are called islands of eternal light, very nice name, but it's really critical when we're actually going there, where the temperature is manageable. And so there's a lot of interest in the poles. And then in addition, there's presence of water in these craters, that's very important. And from an astrophysical and from a science perspective, it's also important to ask this question: is this water really primordial? Is it water from the early solar system formation? It's a secondary water. The original, there are theories that says much of the water escaped and comets are actually from the new class of water. But where do we sample it? This is a place to go sample it. So these permanently shadowed regions, there are craters that are permanently shadowed, never seeing sunlight. You can imagine these are fantastic places to go to observe, look for this sample this early water. And it's not far, you can actually bring that back to Earth for very detailed studies. So this absorption feature is what I was saying. There is this in IR close to 3 microns. You see, depending on whether it's ice, whether it's some other form of water ice, OH, you can get slightly different spectral features. So it's been a concern. And we had a mass spectrometer on board in Chandrayaan-1, which said we found water. We took some time to talk about it because mass spectrometers are not easy to look for. If the water shows up as one of these peaks, you can't read from here, but there is an AMU is the right axis, the x-axis, and at the point where you expect the AMU for water, you actually see it. H2O was actually seen. But any mass spectrometer going to Earth, there's always this worry that there's outgases. Can it be outgassing? Taken from here and gone. Precisely. So that concern was there. So we had to really, and we had only one shot because this mass spectrometer was on a module that was released from Chandrayaan-1 and was ballistically crash landing onto the southern pole. So you had one orbit to really do it. It was not enough to do it. So there were all these things, and so with that in mind, it was decided that we'll extend in the next mission, we'll extend the spectroscopic capability to 5 microns, and then try to use the fact that we have thermal spectrum available there to really do the proper subtraction. So with that in mind, they have done this, and you can actually see this feature emerging very clearly from the Chandrayaan-2 payload after the infrared subtraction. And we can see that signature for water, that absorption feature varies depending on the location that you have. So right now, they are working out the mapping of the strength of this line across the surface of the moon at different seasons and different illumination conditions as well. The synthetic aperture radar, as I mentioned, can look below, and if you look down the left, what you see is the synthetic aperture radar imagery for one part of the moon. And what you see in this colored thing is high reflectors. And what you can actually see, these are craters, but around the crater also you see a lot of reflectors. And what it suggests is the presence of excess roughness, for example. Here is if you look at this particular one too, you see a lot of ejecta in this direction, almost as though you know the direction from which the projectile came and hit it. But it's covered up by regolith. Regolith is this constant plummeting when the moon surface is being bombarded with micrometeorites at a very high rate, daily, continuously. What it does is it actually produces this churning of material, and things get covered with this stuff. So if I look at the same location with the LRO images, you don't see these structures that you see here. So SAR brings that out very clearly, and this is the kind of thing. But the challenge is to really distinguish it from roughness to actual presence of water, and then quantify it. So these are non-trivial, but a lot of work is going on. So this is a spectrometer that actually looks for these individual signals, as the signatures of elements, as I said. And we see for the first time evidence for things like chromium, never really seen earlier, manganese, never seen earlier, and the advantage of this particular experiment is you can quantify it very precisely. We calibrate this, for example, in the lab in URC using known, in some case unknown elements are given to them. I mean, I remember, I think the RBI has released a 10 rupee coin at that time, where we know precisely its composition. So I think I gave it to Athare, I told him, I won't tell you what it is, you do it. And he actually found it. So we found the deconvolution process. I mean, extrafluorescence is a very old technique, but what is not done is when you have to do this in a field condition, where you don't have control on the illumination, you don't have control on the way you prepare the sample, the texture of the sample, the particle size distribution, how to interpret that as a challenge. So, but I think with Chandrayaan-2, they should soon be releasing maps of each of these elements. Oxygen map of the moon, aluminum map of the moon, magnesium map of the moon. And that's a very important input that goes into asking the question about originality from the moon. Now, coming up very quickly are these three missions this year: Aditya L1, exo-solar, and Chandrayaan-3. Chandrayaan-3, already I mentioned, largely is doing the completeness of what was left from Chandrayaan-2. Aditya L1 is primarily a dedicated solar mission. Began initially as a mission around Earth, and then we moved to L1. And with the set of 7 experiments on board, trying to look at answer questions about what heats the corona, waves, or any other processes, the dynamics of CMEs, can we map it very close to the disk of the sun? Other details on abundances, nature of how the flares and CMEs are linked, and so on. So all of these are being addressed using a set of instruments, 7 instruments. Some are remote sensing. They are so we have a coronagraph, and this coronagraph is an internally occulted coronagraph. A real challenge to build it. This institution is the lead institution that's actually produces. We're about almost ready to deliver. It's an absolutely challenging experiment to do. And its uniqueness is the fact that it comes absolutely very, very close to the disk of the sun. 1.05 solar radii is very long-term imaging. And it's challenging because of the fact that scattering from the surface of the primary mirror from where you're going to extract the coronal images is got to be very, very highly controlled. And to control it, you need to have surface RMS at an extremely challenging level. And that has been maybe the best mirror we've ever made is what is there in our VLC. You also have a UV imager that looks at the sun up to 3 solar radii, gives continuous information on its irradiance that is critical for sun-Earth effects and studies, as well as has many filter bands on which you can do other interesting science, and 2 X-ray spectrometers to cover the broad band of a solar flare. And then there are in situ experiments, experiments that actually measure particles and its directions from electrons and protons and heavies, alpha particles, as well as a magnetometer that actually are critical to really combine them to really address local dynamics that actually happen with the solar wind. So this is the VLC imaging part of it. And then spectra is for up to 1.5 solar radii. And so the UV, the UV imager also goes to 3 solar radii. And that is that really addresses this whole idea of what is the corona. And combining that with the X-ray spectrum actually gives you contextual information on the nature of that particular flare, covering both soft X-rays and hard X-rays. I mean, this hard X-ray one is not as comparable as RESI. RESI can also be imaging, but the idea is contextually we actually get both these things in one go. And in particles, you're really looking at KeV to MeV particles, electrons, protons, and ions. Primarily alpha particles, and in particular, when a CME passes by, this ratio of protons to alpha particles is a good indicator of the presence of CME, and so that is being maximized with this experiment. And the magnetometer, as I mentioned earlier. So, uniqueness of Aditya is dynamics close to the disk. I mean, that's a real challenge. I mean, even at 1.1, which many have managed to do, but going to 1.05 is not easy. And then issues about, it also carries a spectral polarimetric package, very challenging things to do. You're moving those slits by a millimeter at 10 micron steps, non-trivial for a space experiment. Spatial resolved disk observations in near UV, onboard intelligence is part of that, and observations we discussed earlier. Yeah. And I want to emphasize the fact that these space observations would be complemented by ground. Gauri with the node is a very important facility. It actually provides megahertz imaging, very critical for various kinds of solar activity. And I think IA has this unique facility. uGMRT has a capability to do solar, complement many of these activities. And the multi-radio telescope in terms of interplanetary scintillation, which of course Mr. Manoharan has been doing that for many years, but now it's not clear. So someone needs to take it up and KFRST will help. And then you have the HRF telescope at Merrick, HRF at Korea, and Labour Solar Observatory, Aries, all these things there, and also magnetic laboratories at ALIPA. So it's, while it doesn't cover the complete spectrum, it makes an effort to really cover a fair amount of it. But it raises important, unique questions for us community in regard to what do you want to do after this? After Aditya L1 is about to go, it's time to start thinking about what next. Now, later this year, we again have a polarimetric mission. This has been is a small satellite mission, is the way we started. It's still a small satellite. There's 2 experiments on board. An X-ray polarimeter. Polarimetry, as you know, has been, X-ray polarimetry was done some 40 years ago. Then they stopped. They measured spectral polarization. And for whatever reason, nothing emerged until very recently. IXP, which both Europe and the US are involved in, which actually showed very, very interesting results. Our plans were to have this launched well before that, and this is less sensitive compared to IXP, but we also added a spectrometer that complements this, and it's a soft X-ray spectrometer, actually a duplicate of the class experiment, but slightly reconfigured, because it allows you to give, polarization is a very weak signal, so you have to stare at the source for not for a few hours as you do in UV and optical, but not days, but sometimes a month. Now, when you have to stare at it for a month, it really helps to really have other complementary experts that also stays at for a month. So you can actually study continuous spectral behavior of, say, an extra binary with regard to the dynamics that actually happens around black holes and so on. So expect, as the experiment is supposed to do that, this has to be in a circular orbit. It has to be rotating, because a polarimeter could have modulations that are actually intrinsic to the instrument. So one way to really avoid that is to rotate about its roll axis. So that has to be done. But then when it's rotating in a certain scenario, it's optimizing it for solar power becomes difficult. So when it's sun facing, you stop the rotation. You charge up the batteries. Go behind this Earth, it starts observing. you spin it up. Every 90 minutes we have to do this. This is an absolute challenge. But then we have to do it. It's really good. This is from Raman Research Institute, which we call as a pre-average experiment, and it provides energy in 8 to 30 keV. And then low energy is 8 because of the fact that it uses a scatterer. It basically uses the fact that you actually allow scattering, and when it's a polarized photon, the scatter plane is actually defined. And so you use 4 detectors around it and map out the azimuthal distribution of scatter as a way of measuring the polarization. And as I mentioned, science interest goes from primarily binaries, pulsars, and many other galactic sources. We believe it will be difficult to really do much extragalactic science with this, given its sensitivity limit here. And if you look at IXPE in conjunction with XPOSAT, POLIX XPOSAT covers this part of the spectrum, whereas the hard X-ray, this is the other area that, IXPE does a very soft part, 2 to 8, and then this picks up from 8 to 10. So we're hoping with the launch this year sometime, we maybe have some common targets that are bright enough for POLIX that could be observed with both these experiments. Well, that would be a very useful thing to do. Because, many a time, the results that we now see with IXPE would show polarization behavior different. For example, how it modulates with the phase of a pulsar, like the crack pulsar. There are data actually from CZTI and ASTROSAT that actually shows something else, but that's at very high energies. We need to know whether it is really an artifact of the data, we analyze the data, or it's really the fact that it's energy dependent dramatic variation in the polarization fraction. And that is the kind of bridging that POLIX is expected to do. I mentioned XPECT is very similar instrument, just broken into 2 parts for computation on the instrument, on the spacecraft. Now, last few minutes, let me just talk about the UV, the future space programs. Clearly, ASTROSAT has been a game changer with regard to demonstrating national capability to really put together a large-scale observatory, multi-wavelengths, operate it, involve community in the form of seeking proposals and regulators, evaluating, scheduling, getting the data public, and the process continues. And we want to build on that. And to build on that, we really need to ask where do we go? The UE instrument that was built here was an absolutely exceptional instrument. And there is a lot of interest to look at spectroscopy. So there is a team here led by Professor Annapurni and team that is looking at spectroscopic expansion of this capability, including high-resolution UV imaging. So that's a serious proposal under consideration. We hope this year we will have a chance to put that into a phase A program. Exoplanets, everybody wants to do exoplanets, and we also want to do exoplanets. There was a large, ambitious proposal that was actually circulated sometime back. I think there has been first phase of study. They trying to accommodate a large 2-meter class mission into our own rockets and to have it launched. But that study continues. It's not going to be an easy mission. You need photometric accuracies that are very large. You need stabilizations of various issues, etc. But clearly, exoplanet studies are very important, and we need to take it up. I think the community will have to really work on that to really emerge with a very strong proposal that can be taken under consideration. And with the discovery of gravitational waves and the realization that LIGO, the 2 LIGO labs, and now Virgo still has an error box that's still large for looking for counterparts. You want to do optical searches for counterparts and quick follow-up. You really need something else that can be provided. So there's been a proposal led by IIT Bombay to really look at electromagnetic counterparts of gravitational wave merger events, particularly neutron star events. And so this involves technology is not very complex, but it still involves producing large number of sensors on 2 satellites to cover the full sky. And so that is also these are all experiments that have been partially selected and funded in the initial phase of it. But the next phase, we have to see how much progress we have and how much of justification we can bring in regarding the timing of that in the context of the science relevance. Something like this is particularly important. I think the EM counterpart, a lot of people in the world are working on this issue. And we need to be sure that by the time we have it up there, these error boxes are indeed of great relevance. There's also interesting interest and some proposals submitted on low frequency radio emission. Primarily looking at the 21 centimeter redshifted EOR signal, which has been claim at 80 megahertz or so, which now the recent results from RRI experiment called SARS. SARS, as said, doesn't look real. And that's there are many ways in which you can actually create such a signature, but it's an important thing. So, but the challenge to many of these such very sensitive radio instruments is the other high radio frequency interference that happens on orbits around Earth. So, what they would really like is to go to the far side of the moon in a lunar orbiter and observe this when it's on the other side of the moon. Now, we can't have a separate mission just for that, so we have to see how to accommodate it. We actually tried very hard to accommodate this in Chandrayaan-3, and 2 months of intense work. The foundation was too big to have it to put it in that. Because you really need to have a ground plane for that, and antenna system. It wasn't easy to do. So these are possible experiments. And the astronomy, again, has to build on what ASTROSAT did. And there is interest for broadband polarimetry across bands. But I think the discussion in the community continues. Every few months there is a meeting, and I think this convergence still hasn't happened. But that's a possible opportunity for potential collaborative activities with the European colleagues. On the planetary side, we have plans to go to Venus, and Venus was actually an interesting object, planet to go to for various reasons. It's studied the atmosphere, topography is not very well known because it's fully covered with clouds. We use radar to see the surface. And of course, behaviors of very high. The atmosphere at about 100 kilometers travels, goes around the planet every 4 days, when the planet itself is going very, very slow. And of course, there are interesting issues, and Venus acts as a target for asking the question about a planet which is in a habitable zone, very similar to what Earth is. How did it transform into something completely different? Are there lessons? Are there really useful inputs that we can learn regarding planets, exoplanet studies, and habitability questions, which are now things of high importance globally? So I think about in 2012 or so, we had actually put together the first meeting that we call the community investors in India to put together a proposal for Venus, and then but right now we're just waiting for formal approval. We need money, I suppose, and we need a priority, so we're waiting. Otherwise, all set to go. It was originally scheduled for a 23 launch because of unique opportunities. The opportunity for Venus comes every roughly about 19 months or so, and liftoff mass is critical. So right now at 31 window is good. It's very good. Europe is going in 31. Americans are going in 31. For China might go anytime, 26, 27, whenever they want to go. But there is a big onslaught of a large set of missions being targeted from Venus. We hope we will have an opportunity to go there as well. So in terms of all of these, what do we have? Challenges. And challenges is as a space program, a space science program, we have a challenge of building a strong user community. And that's very critical. Today we have core users. Okay, we'll get into the nitty-gritty, but that's all right, they'll say. Those who are giving us money will say that's not enough, we need more. So a much greater effort, as we're now doing with reaching out to schools and colleges, students, having a large student involvement in these research programs. I really think we have missed out on that. We really need, I would say, 10 times what we now have regard to student involvement in programs. In PhD level astronomy and space science missions. Broader involvement is critical in the pre-launch activities. And I say pre-launch because of the fact that we do have a fair number of people, as you saw in the ASTROSAT case, who use the data after it's made available, after it's processed. We also want people to get involved further. Your real appreciation of data when it comes in, you can actually see and get to know what's involved, how did the calibration go, what's uncertainty in this calibration, what are the kind of things we need to worry about. And it also allows us to build something faster, quicker. And in that context, looking for small scale activity where you can participate, as you now do with, I think the large ground-based instruments, GMT, etc., have learned how to do that, of really creating global activities, break the problem down into smaller units, and people take up and then we need to really do that with the space mission as well. And of course, international collaborations. We have not really exploited that fully, done a bit, but then no, we'll have to. So my final slide, I just want to really talk about the Indo-French connections. And it's a short list that I say incomplete because I'm sure we missed some things. But the collaboration with France has been always a very unique one. I think it's one with a lot of trust. And it began with the early phase. As I told you, the first sounding rocket had French experiments on it. The Vickers engine that we used quite extensively had a lot of collaborative help from France. On Chandrayaan-1, the HEX experiment, I was the PI of the HEX experiment, high energy X-ray spectrometry experiment. We were trying to do this very rapidly. So I was in Paris for that meeting. At Toulouse, we had colleagues, Olivier Gannot and others who really wanted to work with us, but our time schedule was too tight for them. But you did work with them on modeling the data, and that has gone on. I have not highlighted this, but I just want to only emphasize the fact that there's not a collaboration, but there is the laser ablation breakdown spectroscopy instrument that we now flying on Chandrayaan-2 was actually triggered by when Sylvester Morris came as part of the Chandrayaan-1 discussions to ISRO. He gave a talk about his experiment that was used on Mars on the Curiosity rover. It actually zaps the rocks and you actually get pictures. And we thought it was fascinating. And then I think the colleagues decided to build one for the moon. That was the first one for the moon. And the joint missions that we've had, the successful mission of Megatropics, which was actually a very successful mission, and then Subtle, which is actually something we looked at ocean circulation, are also important missions that shows the strength of the Indo-French program. And in the AO, announced an opportunity for Venus mission, which was also open in 2018. We allowed the globe to participate. We have a proposal that is a joint. Initially, it's a Russian-French program, and now that since we don't have clarity on our program for Venus is not yet fully approved, we will evade that, and we hope we will have chances to collaborate with our colleagues in France. And on future possibilities, these are just my own personal views on it, and that is because, the wide field monitor, X-ray monitor, X-ray, today our SXT has a half a degree field of view. Transient astronomy is everywhere, with LSST and many others, and ZTF, etc. We're constantly looking at most of the sky all the time, as much as we can. X-ray astronomy needs to do that as well. One way to use wide field monitors, and wide field monitors with spectroscopic capability. And that is possible lobster eye. And there are experiments, the Chinese lobster eye experiment recently showed results that are quite interesting. I never thought with that kind of optics you can do extended sources, but you can actually do that. So there is interest in the country as well, and there are certainly companies in France, and if you can connect that with colleagues who may be interested in that. Now, they're looking at optics, for example, in that we supply, we can do the rest of it, we can have a joint mission. But we haven't had any discussion with anybody. I'm just looking at something. And also on the balloon. So now Venus is a very important place to do both orbiter as well as an atmospheric probe. Venus atmosphere is very interesting. At 70 kilometers above the surface, Venus atmosphere is fairly benign. At the surface, it is 90 times the pressure here. It's 700 degrees centigrade Kelvin. Extremely difficult to survive. But at 70 degrees, things are fairly benign. You can actually live there if you want to. There could be microbes out there, who knows? We like to have sample of the day, ideally. So there is a NASA mission to bring it back. I tried to get some people to think about it here. It's too challenging right now. But the idea of a balloon experiment is something we've been thinking about. And so depending on the timing of our mission, that balloon opportunity may arise. And we've had colleagues in France who have expressed their interest in actually participating in the balloon experiment. So there are many possibilities and many more. I think meetings like this will certainly bring them out. So let me close with this picture of Jacques Laveau, who was actually very, very critical in actually helping us in many of our space experiments, right from the Vickers engine. He was a great friend of Professor Yu. He had multiple times come here to discuss Venus as Venus ballooning as a target, and numerous. And so here he is receiving Padma Shri from our president. And I think 2 years ago he passed. But absolutely someone that we think a lot of respect and love for. Let me stop there. Thank you.
Yeah, extensive. It's a very comprehensive talk on astronomy and planetary missions, and also bring into French collaboration. So, those are questions.
So, thank you very much for a very nice talk. So, I think the talk covered a lot about the big missions. But are there plans or calls for very small side missions for giving opportunities to many researchers across Indian universities and institutes? Along with these big missions are separate, but small satellites, small missions. So what are prospects of those?
Right. Good question. I think in 2004 or so, we had a call for small satellite. Aditya and experts had both considered small satellite. It is initially proposed as a small satellite. Has grown into bigger missions. But what you said is right. We have not exploited the small satellite capability to do real science. There have been inhibitions at some level because of the fact that typically a small satellite doesn't give you precise pointing, stability, control. But I think the world has demonstrated it can actually do that. We also have a new platform called the INS nano satellite platform that can actually do that. And so 2 or 3 have been flown. I think what has not happened is maybe an open call for small satellite programs. I think the science office is actually looking into that right now for heliophysics and the future beyond Aditya that has been discussed in the inner group with regard to are there things we can do from a small satellite platform, from a CubeSat platform, where you focus on small experiments that can be done very quickly. For space weather, a very important thing. So I think as a community, we have to think, so I assume tomorrow the call comes in, but how we prepare for it? We may not be prepared for it. We need to be prepared for it. So I agree, we both sides have to work on it. I'm sure it will come very soon. But it is certainly the solely missing point. Yeah.
Thank you.
No questions.
Yeah, well, so there is one big, actually, move going on, and that's called as SGAC Europe.
Oh.
And actually, very recently, that's after the COVID time, many space agencies have come together, and they are carrying out a big campaign of training people in using satellite data for all sorts of projects. Development, research, training, from school level up to experienced researchers. So I was wondering if ISRO is a part of it. It is called as SGAC.
I'm not aware of this, as I have not tried for the last 3 years, so I can't be sure. I haven't heard of it. I mean, we are involved in many of the other global discussions on moon-related thing, on other discussions, but I haven't heard this in particular. I'll check with them.
Yes, because I think this could
But
be
it's
one
primarily
way.
for training on
It's really,
space data.
Yeah, exactly. And really to a big population of different.
Is it sort of driven by ESA? Or is it independent agencies?
There is NS into it, there is EAS into it, so ESA is into it. And I think there are also American industries into it, NASA is into it. So they are private, they are government. So everyone is there. So I was wondering, what is this big move going on? And so this is why I invited you for this meeting. And I was wondering if India would be also interested.
You have to know the details.
Not only to know the details, to participate as well.
No.
Yeah.
That decision
Yeah.
is information details.
Yeah.
Why we'll explore, find out what it is.
I'll send the information.
Sure.
The entire chemical composition of the moon from Chandrayaan-1 is published.
No, first of all, that chemistry is only known for the surface of the Earth, right?
Even then, but
It's a 10 micron surface knowledge of very sample. That is not yet published. That's this year. I hope that will come out because it's involves these things are cores because that X-ray spectroscopy mission has a footprint on the pixel size of about 12 kilometers at best. The sun is very bright. The sun is not so bright; it becomes 100 kilometers. So to really keep doing this, as now that there are more flares, they really fill the surface of the moon with flare time data. It's high. So it's almost there. Yeah.
So what were the main science objectives for Mars orbiter mission?
As I said, primarily it was a technology mission. And the two key things that they were looking for was, one was looking at the signature of methane. That was, from a ground observatory, there's a claim to see. Even now, with Curiosity, there are conflicts. Is it episodic? Sometimes it's there, sometimes it's not there. So this was when the time that mission was being considered. So we had a fabric system there to really look at this thing. And finally we couldn't do it because of some calibration issues, but it was a faint signal anyway. And it had to be, the whole payload had to be developed very, very rapidly. So the short time scale demanded by the technology window, Mars was every 26 months there is a window to go to Mars. And so that's why it was not a very serious science mission, but it still carried this mission. And it's from those, both the mass spectrometer has actually looked at Argon and its changes with various solar conditions at Mars. So that has actually been published in JTR. There's also this connection between the imagery that you got, because it's a full format camera looking at the full disk of the moon, of Mars, could actually use that to really look at the dust storm evolution, and then use other data from other satellites to really link that to loss of atmosphere and so on. Yeah. So it's not the next mission has got to be a very major science mission, unless of course we are also combining that with landing on Mars, which is also challenging. But when the window of development time is short, it is difficult for scientists to really come up with, absolutely cutting edge experiments to do. So that is the point that we have to really be prepared for opportunities. But then, who drives it? These are all big questions that have to be answered.
The thing I was talking about the Space Generation Advisory Council. It's international. ISRO is a part of it. We also have a national point of contact in India.
Okay.
So
who's that?
There's a lady, Megha Chaudhary, and Surender, Konal, and they are the.
I'll ask my colleagues at ISRO.
Yeah, so they are from ISRO.
I'll tell them.
Yeah.
Sorry.
I have a question about moon. Like, is there any mission or any study done by ISRO for the farthest side of the moon?
We have not as of now. We've been focusing more on a polar mission. There's a mission that is being discussed with the Japanese space agency, JAXA, for a polar mission that lands at 89 degrees south latitude and to have a rover that will go into the permanently shadowed crater. So that is completed phase A now. We have to now get a clearance to whether we should go to phase B. So that's it. After that comes, going to the far side has new challenges, particularly having to have another satellite for relay data, commanding and data. So the Chinese mission that landed on the other side actually has that satellite position already. It's a much more expensive and involved program to go to the far side. As of yes.
Thanks for a nice talk. So it's very curious, it's very exciting to see the different experiments covering different frequency bands. But my question is about the sub-millimeter and microwave frequency bands. So I would like to know the status of CD part kind of experiment.
Sub-millimeter and microwave, yeah. These are clearly important areas, certainly for astronomy. We think that's very important, maybe for other applications as well. Sub-millimeter has this, the detectors are not easy to pick. So there is a program in the country, in this application center, there's a team working on a sub-millimeter ground-based telescope to do carbon monoxide mapping, etc., which we hope will go slowly in the sub-millimeter mission. That's the time we can actually do it. Ideally, if we had a sub-millimeter sensor on our Venus mission, it would have been fantastic to look for phosphine signatures. But that's the challenge. Right now, so we're only at the level of laboratory and ground telescope. Hopefully, in the next few years, we'll have that established. then we build from that. So it's a very important area that we need to move very far out. So I was just discussing with Divakar Maya, isn't it? Okay, Divakar, about the possibility about in Mexico they have a large millimeter wave facility, and they have a lot of time. So I was trying to look at the possible trading that time for possible role in future programs that will allow us to really get used to. So see what happens often is when we don't have a sub-millimeter telescope, we don't do sub-millimeter science at all. There need not be any more true. We can actually work with it. So what I said, look into it. So right now we don't have it, but I'm sure it will come up because they all have very unique ability to look for the important questions they were all asking. And today in astronomy, you can see how ALMA is actually producing fantastic results. You can't avoid it, you have to have it, so we do it.
Thank you.
Long live India and France friendship.